Anyway, so we want to make sure that this actually works correctly. At this point, we have our shellcode. The next step is actually to jump to the shellcode, and therefore, the buffer that we're going to overflow is the shellcode followed by the address of the shellcode, so that when we reach to the return address, we will jump actually to the shellcode. So more graphically, if this is the buffer that you overflowing from left to right, Lucas, is that okay? First you have the shellcode, and then you have repeatedly the address of the shellcode, so that when you actually overflow the return address and you actually return, you would jump at the shellcode. So the problem is that most of the time, you don't really know where the buffer is. Sometimes, if you can debug it and it's a local attack, like you will have in homework 3, it's very easy to see where the thing is. The problem is that sometimes you pass parameters on the command line, and that can affect where your actual stack ends up being by a few bytes. And here we're not talking about you kind of have to be there. You have to provide the exact address of the shellcode. You cannot, there is no room for mistakes. And of course, this is in the assumption that you don't have stack randomization. As we will see, once you have layout randomization in memory, the problems are very different. And we also have to guess the sort of the offset of the buffer with respect to the stack pointer, so we know where we are in memory. A way to make this a little simpler is to put in front of the shellcode no operation. So the byte 90 in Intel x86 means do nothing, and it's 1 byte. So if you put a bunch of 90s, it doesn't matter where you fall into this, you will slide into the shellcode. Okay? In fact, this is called a NOP sled, exactly for that reason. And that allows you to be a lot less precise, because fundamentally you can end up here or here or here, and in any case you will perfectly reach the shellcode. And so your buffer address here doesn't have to be super precise. You just say, hey, point somewhere, and hopefully you will get into the knob. And in some cases, that knob sled can be ginormous, in which case, you can even get to a point where even with stack layout randomization, if your knob slide is big enough, you had a good chance, if you can do multiple attempts, to actually end up in that knob slide. So if you look at a program like this, it's one of the most simple version of buffer overflow. You have just a buffer, a string copy that takes a parameter and copies in this buffer without checking for boundaries and returns. And this simply passes, the main function simply passes the argument, the first argument of the program to this function. And so obviously, by passing a string on the command line that is bigger than 512, you will overflow the buffer and you have control on the EIP. So if you look again on the paper that we were talking about, smashing the stack for fun and profit, what they do fundamentally is they create, and I put the code here for reference, but fundamentally this is just creating a big buffer, and is writing the shellcode in the middle, and it's prepending it with NOPs, and is following with some offset on the stack. Okay, so with the potential address of the address. And you can see there is here a simple instruction that simply put the stack pointer in EAX. So this function simply returns to you the value of the stack pointer, because when you put something in EAX, and is the way to return a value from a function. And so here, fundamentally, it takes the value of the shellcode and puts it in the value of that offset from the stack, this address. So you get the stacks, decide an offset from the stack pointer. That's the address that's going to be used to overflow the actual return address so that we can jump at our snoplet. And everything is put in this command line. Mostly it's just the way the author does it, and it's a way so that you have in your environment, and you can pass using an environment variable, and you don't have to deal about weird characters because there are a lot of binary characters that are unprintable. And so the basic idea is that you call create egg, you're dropped in a bash environment where there is this $egg environment, and you pass it to the vulnerable program. And if the vulnerable program is set to ID root, you will get, the £, which means that you have root access to the system. It's as simple as that. Of course, you might sometimes find yourself in a situation where you'd have to overflow small buffer, so you cannot put your whole shell code into the overflowing thing. Well, then you have to put your shell code somewhere else. Sometimes it could be, of course, in the environment variable. You can have not only the egg to pass it to the program, but in the environment variable, you can put the shell code. And of course, if your stack is executable, which might not happen on your Linux machine that you installed yesterday, but it might happen in your IoT device that you're analyzing recently, then you can put the shellcode in the environment, and the overflow is only with the address. And so I put here as a reference the code, and the basic idea is that it creates the same thing. It generates an address which is an offset from the stack, and simply fills the overflowing buffer with that address. But this offset from the stack, instead of pointing to a region in the stack, actually points to the environment where the whole nopslad and shellcode has been stored, so that you will jump into it. Similarly, you can see when you create env-egg, so the program that I just showed to you, you can see that there is the ret value is simply an environment variable with the address repeated many, many times, okay? And that's what we pass to the program. But then there is also the egg variable, which actually has the shellcode there, and you can jump to it, in memory. Of course, if that area is executable. So this is just an example, and it's the step-by-step description that is in that very well-known paper about smashing the stack. Of course, there are infinite variations of this concept. You can look at a generalization of memory corruption as sort of an exploration of what can you override, what causes the override, and where it's overwritten, okay? By composing this, you can get at different situations. And we just went through a qualification, and in these super sophisticated competitions, some of the stuff is incredibly complex. You don't override the return address on the stack. Most of the time, you have a function pointer somewhere that is hidden that you're able to indirectly affect by 1 byte or 2. You can get in very complex situations. So, for example, when you look at what is overwritten, we saw the return address, but an interesting thing to control is also the frame pointer, because the return address has that sort of immediate gratification aspect that you jump to your code. But with one level of indirection, controlling the EBP or the frame pointer allows you to fundamentally, on a return, move your frame pointer to a new stack frame that is now under your control. And that stack frame, if there is another return, can have the return address that you want because you created that particular stack frame. And we will see an example of that. Also, you can override a pointer to a function. If you have in a data structure a pointer to a function that does specific things, you can make that function to jump to whatever you want. Also, the pointer to data, being able to have something that should open, a variable that specify, home, Vigna, mail. You decide to overflow that variable with a different value that will make that program open, etc shadow or some other security critical file. And also, just variable. Imagine, there is a code that does setuid, and you're able to overflow on the stack the value of the variable, so is, instead of dropping privilege, keeps privilege. And now it's operating in the assumption that it drops privilege, but since the variable was set to 0, the dropping never happened, and now you have the possibility to exploit a confused deputy situation. Also, there are many causes for the override. We, of course, looked at the unchecked copying. But also array indexing is incredibly powerful because an array index is nothing but an offset for a pointer. And one of the assumptions, for example, that can happen is that people think of arrays as arrays with positive indexes. And they very seldom check, oh, is this index negative? And suddenly they don't check for the negative value. They don't only check that it doesn't go beyond certain boundaries. Suddenly you're providing negative values and you're accessing random memory below the base of the array. Integer overflows are also very interesting. Those are the tricky ones that happen when either you, of course, increase an integer value and unsigned above its top limit, and that integer goes back to 0, which can cause very interesting situation. Or when you convert or compare signed and unsigned integer without care, and suddenly you have a negative value that is compared to as an unsigned, which becomes a gigantic value, and we will see example of that. It can be very tricky. And of course, loop overflows, when you don't check enough of your looping exit condition, and you end up spilling your data on the heap, on the stack, wherever you are. And of course, you can override the stack, the heap, the data segment, the BSS, the GOT, and the detours we saw. Everything that is writable in your environment can be the target of an override. Of course, writable does not always mean executable. Actually, as we protect operating systems more and more, we have this concept of everything that is writable is not executable. But there are always ways to eventually, or always, oftentimes there are ways to actually end up executing code. Yes?
You mentioned earlier that like a modern Linux distro wouldn't have executable stack, but an IoT device might. How come that is?
So that's a very good question, and there is no specific reason why, but it's in computer science, especially in security, what happens is that there is a very complex system like Linux, and people start using it for security critical things. People break it. People say, oh, we should stop these break-ins because we had buffer overflows for years and years and years until we had by default non-executable stack and everything else. Then a new platform comes in, and for example, it's a very simple type of ARM processor, and they decide, oh, we have to keep the code base very simple and small. Let's not add stack protection, because who's going to attack, a Garmin watch? Okay, and so they tend to simplify the operating system because of size, because of complexity, because adding security in general also, adds possible problems. The system might stop, and so sometimes they reboot the concept of, oh, let's have everything executable, let's keep it simple so it works all the time, but then, security becomes an afterthought. So these techniques are still very applicable. Is that answering your question?
Yeah.
So going back to what is overwritten, any reference to a value can be a security vulnerability if it can be overwritten and it's used in a security process. We looked at example of pointer to strings, integer variable, and we will see more in detail how you can actually manipulate the base pointer or in order to achieve wherever code you want to execute to be executed. And of course, the value of a function pointer, especially in the GOT or in the detours, can, of course, allow you to execute randomization. When we talk about, for example, a good example of something that is weird that people do not perceive necessarily as an issue are long jumps. Long jumps, how many of you ever used a long jump? Okay, one person in the class. So long jump are a very weird construct that is used to, for a number of things. You can use it for example, handle specific error conditions. And the basic idea is that set jump allows you what it's called to save in a data structure the content of the CPU fundamentally, okay? And a long jump call restores that context, okay? And so the first time long jump, is called is, returned X. So the first time you call, it returns the first time that you invoke the set jump, it returns 0. So you know that you just returned, you set up the environment. When you do a long jump, then instead returns a different value depending on where you are. And an example here will clarify things a little bit. So you create this data structure, is a jump buffer, so it's a data structure, a struct that really has inside, as we will see, all the register. And here is say, hey, if set jump is different than 0, that means that I just return from a long jump. So the first time I execute set jump, this will return 0. That means that everything is good. I saved in that jump buff environment the state, and I will proceed to execute function 1. Then I go to function 1, and I'm doing my stuff, and I will check for some error. And if I see that I'm in an error, I want to reset my state. It's like I'm executing this again. Everything gets forgotten of what I've done. I'm here again, but instead of returning 0, I will return this value error 1, say 5, okay? So this allows me to say, hey, I just reset because there was a problem. By the way, the return value was error 1. If I do that in error 2, this, again, I will restore here, exit with a different error. But the cool thing of this set jump, long jump is that really you can say, save this state when I was here. If something bad happens, make it look like I just returned here again. Sort of like, it's like a, reload or, rewrite of your environment. And this is achieved in a very simple way. So there is actually, the data structure contains the various, the various register that needs to be saved. And so you have something that is saved, and exactly the signals that need to be remembered, the signal mask. And of course, when you do a long jump, fundamentally you go to your environment, you restore the registers, and you jump to the address of the place where you set the environment. So you're really restoring the register and jumping back. It's a way to completely reset your system exactly as in the case of performing a set jump, but with a different return. Of course, you can see that here there is this restoring that can be influenced. Suppose that now you can overflow the data structure. So imagine an attack where you have a long jump, a set jump that fills the data structure with the current state, an overflow that gives you control of the content of that data structure, and then a long jump that restores that information. Suddenly, you have full control because of this final, this final line, sorry, I'm jumping around the wrong place, where you jump to whatever was saved in the jump buffer as the new program counter. If you can override this value, you jump to wherever you want. So you put your shellcode somewhere in memory, you overflow the jump buffer, and suddenly you have full control of the system. So the lesson learned is just an example, but people not always understand that data structures can be as critical for security as return addresses and frame pointers and so forth. Yes?
So how do I make sure that it's not overwritten?
Well, I mean, you look carefully to your code and you try to identify situations in which it cannot be overridden. From an automation point of view, there are several countermeasures. For example, things that would order on the stack parameters and data structure to prevent this type of overflowing. But in general, unless you have, for example, system that verify the integrity of a data structure. So you decide this data structure has been set in a separate stack. I set the MD5 value of this thing. And before restoring, I check that this has not been manipulated. Unless you have something ad hoc like that, it's very difficult. So be careful.
Basically the same countermeasures of
Pointer, point guard, and all that. Yes.
the same as
It's integrity.
for the
Absolutely. Absolutely. So also check for something that is overridden. Who can find the problem with this code? So it's main, two password buffers, but they're copied, and this guy has been very careful in using the N version, so it will not overflow the buffer with more than 512 characters, and then calls the check password function that copies the password in the buffer, and everything should be fine because the password is the buffer is 512, and I haven't copied more than 512. So where's the problem? Yes?
I don't remember exactly, but the string name copy put it to an angle after 512.
That would be fine.
No, if it puts it after, it's not.
It's not, but it would. You're right. In this particular case, it would work for a 1 byte overflow. That's true. You would be a 1 byte overflow, which in this particular case, being that buffer against top of the stack, if the no reordering will allow you to do the super cool 1 byte EBP modification that we will go through. This I think is one of the coolest things. But that's not the case. It's even worse than that. Here.
If you can modify password in between when you copied it and when you check it again.
But this is the code. How do you modify it? Yep.
The other thing is that it depends on the stuff that I know. If I just don't enter a password, just a zero-length password, does it just check it in? Does it overlap with the thing it checks it in?
No. Yes.
So actually, str copy, if it copies 512 byte, would add null byte.
Exactly. String and copy does not add the null byte afterwards. If you reach 512, we'll just say enough. I don't copy any more bytes. But since these two are one after another, since there is no 0 bytes between the two, when you copy password, you will copy up to 1,024 characters in a 512, and that's your overflow right there. Okay. So it's called a non-terminated string overflow. So and it's as simple as first print your 512 A's, fill the first buffer, and then send the second one, okay, the argv2 if you want, that has more, and then the address of the buffer where to jump. I'm assuming that your environment contains the shellcode, and bam, that's as simple as that. So null terminating strings can be tricky. And also you will see in exploitation can be painful because, whenever you find a 0 around, it will block copying. So, these 0 bytes are a problem that is recurring. So, yep. What was the problem? Okay, suppose that first I string copy 512 characters on the stack. And let me... So So this is the stack, and it's of course growing this way. And here is the two variables, 512 each. So we have, let's say, username and password, okay? And this is the EBP, saved EBP, and the EIP, okay? Saved EIP. So first you string copy in password 512 character, and it will just stop here, right? But it fills all, and there is no zero afterwards, because you give exactly 512, and string copy will stop. If I give you as argv2, I'll give you 1,000, it will copy only the first 512. And the second one is copying the username, and so you fill also this completely. And you can put also a nice zero here. It doesn't matter at this point, okay? The thing is, when check password is called, it will copy the parameter that is passed is the pointer to the password buffer. And so string copy will start from here and go like this until it finds a zero. But instead of copying 512 in that buffer, we'll copy 1024, causing an overflow. So one interesting thing is many years ago, when buffer overflows were the big thing, a lot of people took string copy and add n and the size of the buffer. Because now there were all these checks that will say string copy is bad. You have to have string n copy. But using string n copy without care can cause all sorts of problems because it's a non-terminated null string. Not only, and this is true story, reviewing code during a pen test, if I remember, I saw this piece of code, string copy in some buff. There will be source, and it was like string len of source. Okay, this was it was a beauty because it was somebody who was obviously told never to use string copy, but always use string and copy, and you see the problem there, right? This is equivalent to a string copy because instead of being string length of the receiving buffer, is string length of what you're copying in. So you copy everything in. This is true real world code. Okay? Yes.
This is not that question, but in the same years this happened, there was a discussion on string copy on the kernel mailing list that lasted for more than 50 emails, and at the end of that, the FreeBSD people forked string.h. So now string.h for the FreeBSD kernel and the Linux kernel are totally different.
Okay, interesting. I didn't know that.
For this reason,
Okay.
string copy is
Crazy. Yeah, absolutely.
so actually the kernel has a modified version of string copy that goes on the phone.
Interesting. I didn't know that. Okay, so always make sure the strings are null terminated. That's very important. Yes?
So I'm a little confused. What's the goal of the attack? Is it to overflow buffer or is it to get the password?
No, to overflow the buffer. It's to confuse the system into thinking that this buffer that was supposed to 512 instead will be interpreted as 1024 because there is no terminated null. And string copy is a function that just say, I'm going to keep copying until I get to a zero. So if you take away that zero, it will keep on copying.
And so if you put some shellcode or something in the username, is that what you could?
You could do all sorts of things. You could, this become your overflowing buffer. When you call the new function that check the password, we'll have a save EP, save EBP, and this will be the stack, and there's going to be whatever the my PW buffer was here, okay? And so this thing is now going to try to be copied here. So first, it will copy the password, okay? And then the first 4 bytes of the username will be overriding the EBP, and the second 4 bytes of the username will override the EIP. You can put the code here, you can put it after. 512 is quite a bit of space, and then you have full execution.
Thanks.
Another even easier way of overflowing is index overflow. So These are very easy because fundamentally they give you what we call arbitrary right in most cases. That means that you can set in memory any value or almost any value to whatever you want. And once you have that, you don't have to overflow. We just set that value to, the address of my shellcode, and you're fundamentally done. So you can do all sorts of different things. Of course, that if you have a type of array that is there's not just integer or 4-byte value, but it's more of a data structure, then you have to follow the data structure and take care of the problems. But this is an example. You have something that simply, this is a very stupid program that take a value from the parameter, an index from the first parameter, a value in the second, and put it in the array, and you can simply pass 11 and the address of your shellcode, and you will have execution. Because if you think about it, this array here of 8 bytes is on the stack. So once again, this is the stack. So here your EBP, EIP, and there are here 8 bytes for that array. If I can say, hey, go to, instead of byte 8, go to position 10 or 11, then I can just override the EIP directly. It's just an offset from this base address. So your offset was supposed to stop here. You go up to here, and suddenly you can change the EIP. So these are, in some cases, are absolutely trivial to exploit. Of course, lesson learned, check your array bounds, both negative and positive, okay? Because they can be, of course, abused both ways. This is really important. An interesting one is integer overflows. These are tricky because sometimes the problems are hidden in the semantics of the language and how they're compiled. But it can be caused by a bunch of different things. First of all, there is purely loop around. You have something that is a signed value. You add this is the largest possible signed short integer that you can represent. You add 1, and suddenly you have the biggest negative value that you can represent. And so for a programmer, this is really, for you guys, of course, you're trained by the best to write the best possible code. But for an untrained computer scientist, the idea that you get to a thing and it's a very big value, you add another 1 and you become suddenly a very big negative value is counterintuitive. We like to think of numbers that grow, continuously. Or we can have something where it has reached the sort of the range of representation. You add 1 and you loop back to 0, which is something that usually we're a little more easy with. This is usually a little more tricky than this for most programmers' mind. And of course, we have this idea that you have expansion where you have something that is a signed value, -2, that is going to be represented as it's going to be assigned to an unsigned long value. And so now this negative thing is expanded and transformed into a positive integer. And so it's really 4 gigabytes -2, fundamentally, as a positive value. So something that was really small suddenly became something really gigantic because it gets expanded and reinterpreted as unsigned. Yes?
If you use the -w all flag for C, would it warn about that last?
Yes, I think so.
Okay.
I think so. A lot of this warning, a lot of these situations would be identified, but it's not always that easy. This is a classic example of a buffer integer overflow. So here you have the max is the size of the buffer, and the length is actually taken from the parameter, but is a signed value. Okay. So here it's if len is less than max, then copy because it's safe. So you say I received, a parameter of length, okay? I check that is less than 512, and only in that case I will be able to copy the thing. Seems safe, right? So where is the trick here? Yes?
You just go ahead and give an input that's slightly longer than the max of the short. And if it's that long, eventually it's not around to negative 2.
And what is that number? How big does it have to be?
I forgot, but it was on the last slide. 2 to the power of 16? Well, 2 to the power of 16 plus 2.
So close. Any takers? That would be if for an unsigned, right? To 32,000 and some, right? And that's correct. So in this case, if you pass something that is 33,000, suddenly your len, is minus something which happens to be less than max, and so the check is passed. But when you actually copy the value, the buffer is actually 33,000 long, and so you can overflow the buffer. And the interesting thing is one of the most interesting denial of service attack was actually caused to this, the teardrop attack. So this is an attack that exploited the way in which fragments are reassembled in the kernel, and you would send one packet or a series of fragmented packet, and it would cause a kernel panic, and you would shut down the machine. And it worked because if you look at this code, fundamentally, you have, count is the number of bytes, len is the total size of the datagram after reassembly, you have the pointer in the buffer where you're putting the various fragments, and this is the list link of fragments. So you start, going through the link, and you say, hey, if what I have so far plus the length of a segment is greater than the actual length of the whole thing, this could be another attack, right? The ping of death. So you would complain that you're trying to, remember ping of death was like when you would reassemble all the datagram, you add another one to create something that is more than 64K, causing a kernel panic. This is post ping of death. They have a check for that. But they didn't have a check for something else. So if everything is copacetic, they would do a mem copy at that offset for the length of this fragment and at the point where the fragment is stored. And this is perfectly fine. The problem is, how is this FP len computed? It's just a parameter of the fragment. Actually, during reassembly, they check for possible overlap. And so what they do, they say, hey, the end of my fragment is where are the offset plus the total length of the header, of the fragment minus the length of the header of the IP packet. So this is where I will end my thing, right? But if there is a previous packet and the offset is less than the end of the previous packet, okay, that means that I have an overlap. So what they want to do, they want to sort of throw away the parts that overlap so they don't have to, write it. And so the overlap is calculated at the previous fragment end minus the offset. So this would be the actual size of the overlap. And then they increase the overlap, and the end becomes computed as, where you see here, the end minus the offset. The problem is when you get a packet, and then you get another one, and the packet is smaller than the size of the overlap. Okay? So if one sends a fragment that is actually, the offset, if this value becomes negative, it will be interpreted like a gigantic amount because it will be interpreted as an unsigned integer when it's time for copy. So by crafting a fragment that would actually be within the overlap, smaller than the overlap itself, you could cause something like that. And so in your thing, for example, you would have a first packet, and then we'll have 8 byte at offset 24. They would put the end of it at 32. And so you see this is 32. So your end is 40, which is greater than the offset. So the overlap is 40 minus 24. Okay? But the offset now, the pointer end becomes the end minus the offset, which is 32 minus 4, so a minus 8. And because of this minus 8, now the length is a negative value, will be interpreted as a unsigned value, which is very big. Copy a bunch of crap on the kernel, and here you have your teardrop attack. This was many, many years ago, but a very cool way to see how subtle this condition can arise, how subtle is to, how careful you have to be in understanding every integer, how it's used, how it's defined, what are the conditions that could, bring it to be negative. It took the kernel developer quite a while to find this attack, and once you see it, it's obvious, but you have to see it first. So you have to be very careful. This is the lesson learned of how to use and assign your integers. And remember, integer overflows can make a large signed integer become a large negative value, or a large unsigned integer become a small positive value for loop arounds and things like that. Yes?
Are there any automatic ways of either preventing this or solving it?
Yes. There are compiler checks. There are tools that in the compiler or as addition to a compiler will verify and will keep track of the context in which certain value are used. And they will be able to say, hey, you just use this as an unsigned value, and suddenly you transform it into a signed. Maybe they cannot tell you, hey, this is exploitable, but for sure they can tell you, hey, human analyst, look at this, because this could be problematic. The thing is, it's easy to identify cases in which you have like a type problem. But when you have a value problem, and if the value would always be small positive between 0 and 16, you would never have a problem. It's only when you have this super weird corner case, who would send you a datagram that is smaller than the overlap with the previous datagram. Makes no sense, right? And nobody thought about this corner case. And in this corner case, it's not that the type is wrong, it's that that value becomes negative and can bring to this condition. Those cases in which is the value that changes are more problematic to analyze. Okay, we have another few minutes. And then we have loop overflows, which are fundamentally situations in which you have a loop that copies stuff, the boundary condition is not checked correctly, and suddenly you spill stuff around the stack. A special attack is the off by one loop overflow. This is because, once again, it's more about us as programmers and our mental model of what loop is. It's very difficult sometimes to start from 0, and then you want to copy 256 characters. You are inexperienced, and instead of say less than 256, you write less or equal to 256. So you're actually copying 257 characters. So this off by one, when you write one too many, is very interesting. Interesting if you have a buffer like we had in the previous case, and you are right against the EBP, then you can actually create an interesting case in which you can control of execution even with just 1 byte. And we will see the example in 10 minutes after you refresh, get some coffee, like I will, and we'll be back. Okay. All right, this is one of the things that I they're like quite a bit of how crazy exploitation can be. So look at this. You can see the problem, right? But the cool thing is like this function is called, and the data is copied in a buffer that is 256. But of course, the problem here, as you immediately caught it, is the less than equal, right? You cannot, if you do a less than equal to 56, you're actually copying 257 characters. And since that buffer is right against the saved EBP on the stack, you're going to overwrite 1 byte of this guy. So let's look at what that means. So here you have your function. And this is, if you remember your epilogue in a function, fundamentally moves into the ESP, the EBP value, fundamentally annihilating the current frame, and then pop the saved EBP into EBP, restoring the frame, and then perform a ret that will take the saved EIP and jump to it. Okay? So at the very beginning, you have the program counter is a beginning of this thing, and the stack pointer is whenever it is. For example, here, there is our buffer, some free stuff, and EBP is pointing to the saved EBP. So in the style of animation, the moment we move ESP, you can see that ESP now has been set to the value of EBP, so they point to the same two things, where right after this instruction has been executed. And so we got rid of everything. And what follows now is that ESP, the EBP is popped. And so EBP now points up there at the frame where there is main fundamentally. And now the stack has the saved EIP. So when we do the ret, we jump correctly to the right place, and we return into main. Nothing is bad at this point. Okay. The cool thing of this attack, it allows you to actually, when you overwrite off by 1, you copy your data from 0 to 255, and then you control 1 byte of the saved EBP. Okay, only 1 byte. That's a 4-byte value. We're talking 32-bit stack at this point. And so by controlling this, of course, you can decide, for example, where your EBP is. If you think about what that means, think about tracking the frame pointer. So when you do move ESP EBP, that means you put the value of EBP in ESP. So at that point, we can control the stack pointer if we have the frame. When we do pop EBP, the stack pointer is now the frame pointer plus 4 byte. If we could control the frame pointer, now we know that the stack is frame pointer plus 4. And when you do ret, what happens is that we will jump at the value that is popped from the stack on something that we control plus 4 bytes. So the program counter becomes the content of the frame pointer plus the 4 bytes. Right? Because that's where you have just popped the EBP. The interesting thing of exploiting this off by 1 is that you have to first cause the overflow, have one epilogue, function epilogue, in which you do the move ESP, EBP, pop EBP ret. At that point, you can set up shop the way you want, and on the next return, you will be able to have full control and execution. Okay? So imagine that our attack buffer, remember the 255, is some knobs, the shellcode, the address of the shellcode, and then the lowest order byte of the frame pointer. So we're going to write all this, and we have to make sure that this buffer will be executed. Wow. How? So this is what we can do. We are overflowing this buffer. We have 256 bytes from 0 to 55. Okay? We want to set it as, and we control this 1 byte. But we want that after we return from actually main, okay, not when we return from this, but when we return from main, this stuff gets executed. So fundamentally, we have to convince that the return address when we return from main is actually this. Okay? And we can, because since we control the saved EBP, instead of returning to the EBP of main, we will return some elsewhere so that when main returns, it's like, oh yeah, this is the save, whoever called main, this is the return address to jump to. So when main finishes and returns, we'll jump to our thing. Okay? Of course, it's not as simple as that. So first of all, we have to understand, where is the stack? And what you can do, you load this thing in the debugger, the function, and you can say disassemble our function, func, okay? And you can see that here there is, the classic entrance of a function, allocate some stack, etc., etc. And here you can put a breakpoint and say, hey, show me where is the, you see, I put in 3D, so right after I enter the function and I allocate the stack, this is my 255 buffer plus local variables, I break exactly at this point in the code, and at that point I say, hey, give me the value of ESP. Now I know that the moment I enter the function, my buffer was BFF FFC60. Okay? You're familiar with using, you will be familiar with using the debugger quite a bit. Okay? So you know that the address, okay, there is a counter. So the address is going to be the current stack pointer plus 4. That's where my buffer starts. Great. So at this point, we want to find, we have to determine exactly the address of the address. So we know where the stack is. We have to add 256 bytes, okay? And then we had 4 bytes for the size of the pointer, okay? And so the address of the code, remember it was BFFFC60. We added 4 for the integer. We had 255, okay? And then we have to detract 0 because that's where we're going to put our end address, okay? So that is the address where we have the address of the shellcode. Okay, so just to give you an idea, going back to our, this is the address of this. So we went here, we accounted for 4, the stack was here, we took away 4 because they were an integer, then we went up 255 to here, we went back 4. This is the address where we have the address of the shellcode. So this is BFF, something that I don't remember at the moment. This is BFF FF D60. Okay, great. So now there is one aspect that is interesting is that with high likelihood, the most significant 3 bytes of EBP and the address of the shellcode are the same because they're very close to each other. So the 3 most, they're probably within 256 of other. So let's assume that just for simplification, okay? So we want EBP, the EBP that we're going to transform and control, to be the address of the shellcode minus 4. So, and this, imagine this is pretty clear. If you look at this, we have our shellcode, we put our, the value. We want that when we return from this, okay, our EBP is going to be exactly here because we wanted to restore EBP and then do a ret on this value. So this value, instead of going back to the main frame allocation, should be here instead. And in fact, we want to set, these 3 are the same. We want to put 5C here so it points to this. So now when we restore the EBP, instead of regularly restore to main, we restore the EBP to here. And main hopefully will not, because suppose the main is using a bunch of local variables, is going to garble this, thinking that it's its own part of the frame. And then sometimes you have to account for it, so you cannot put your code there because they're going to be mangled with. You have to jump around it and do all sorts of shenanigans. But in the easiest possible way, if main simply returns, and we go here, and then returns again, then we'll restore this value to some crap we don't care about, and then do the ret to this value, which happens to be our shellcode, and will be executed. Okay? Now it's animation time. Yes, question?
The byte that we're overflowing is the LSB?
Is the least significant byte, correct. Is that clear? And the most difficult part here to understand that when you overflow the EBP, it's almost like a delayed attack. You don't get the immediate gratification of overriding the return address, but you set up something that later will confuse the mechanism behind it and bring you to execution. As you will see, also heap attacks are like that. Oftentimes with heap attacks, which I would consider one of the most complicated attacks, you have to set up weird chunks in memory so that later, when somebody goes there and frees that chunk, start playing with pointers in the wrong way and start overriding values under your control. But let's see how this works in practice, because this is, yes? Yeah.
Kind of the same prefix as what you possibly have without overwriting the 0xyz.
Correct.
So does it mean that if you would have like longer doc that would make sure that PFFFFD is kind of no more reusable?
So if these 3 bytes, you see, this is the safe EBP. We want this to become this. If the 3 bytes are not, for example, that could happen if there is a ginormous frame, then not exploitable, for example, in this particular condition. Most of the time, you could have situation in which they're close, but they're actually at the boundary of that. Sometimes you can play that by, if you control the environment, you can make the environment bigger and squash the initial of the stack a little down so that you're not exactly in that boundary. Of course, if the frames are very, very big, which very seldom happens, then you might not be able to exploit it. Very good question. So here we are. We have overwrote the last byte of the saved EBP. Okay, and the cool thing is now we're going to exit from func. As we will see, nothing really bad happens here other than the first step, I move ESP into EBP. So my stack pointer is pointing here. Everything is normal. But then when I restore this, the stack goes up and delete from the frame, deletes, accounts for it. The frame, the data is still there, thank God. Now I'm going to pop EBP. So this is the cool moment where the attack really take place, because now you see the EBP, instead of going up there where it should, it's right here where we control it, and then we return, okay, to losing the saved EIP. So the first return from func doesn't execute our code, goes back to main, whoever called us, okay. So you can see there is main, and then main eventually will return to 0, okay. So main will go through the same identical procedure. So what happens next? So when func returns, EBP points to shellcode and address of the shellcode -4. And when main returns, now the same thing happened. ESP will take the value of EBP. Pop EBP increases ESP value by 4, so now points to the address of the shellcode. And when you return, you jump to the shellcode. So here it is. You can see that here, now we are in main, okay, but our EBP is in the wrong place. So when we first, do something weird with the stack, instead of deleting the frame of main, we bring the ESP here. Who cares, We don't care about cleaning up. What we care is that EBP is going to be popped and ESP is going to point to this as the next value, as you can see here. And that suddenly, when you do ret, now you return into your shellcode, and you have execution of the shellcode here. Okay? So lesson learned, even a byte can hurt you. So even a single byte can hurt you. So you have to thoroughly check your loop. And one important thing is this idea that you should not have user control input determine, in most cases, the loops. For example, one thing that we do as research is identifying complexity attacks against application. And one classic complexity attack is when you can actually control the loop variable of a very expensive operation. So for example, there is a server, and suddenly the number of iteration on encrypting this large buffer is determined by my input. Now I can say something, oh, do it 1 billion times. And suddenly the server is doing something very expensive many, many times and can create a denial of service attack. And these are not very easy to detect. And also remember that the off by one can cause crashes, but also execution of arbitrary code. Another interesting way of overriding thing is format string vulnerabilities. This is the beauty of variadic function and super interesting trick. You have used million times printfs. Printfs are cool, are variadic. If you remember variadic, we use the CDECL standard for invoking functions because it allows us actually to use variadic functions. So functions that can have a variable number of parameters, okay? Because it's the caller that knows how many parameters are passed that does also the cleanup, and so you can do that with the disadvantage that you have to do the cleanup in every location of the call. And so you can see that, but the caller doesn't know much about it. So if you do printf hello string and you have a name that matches, perfectly fine. So, but if you can control the format string, okay, this is really bad. This is really bad because what if, you print buff assuming that this is a constant, is, a log entry or something like that. But what if it's under the control of the attacker and can give you %d, %d, %d. Suddenly the caller say, oh, I see 3 parameters here. I'm sure the guy that called me up there put 3 values on the stack that are going to pop up and print, okay? But those parameters are not there. But the caller, the callee, doesn't know that they're not there. It's just going to go on the stack, get 3 values, and print it on the screen. Try, it's very simple, Just do a print buff %d, %d. It's not going to tell you, oh, no, I don't have those values. It's going to say, hey, found stuff on the stack, here it is, and I print it. And one say, well, first of all, is bad because this, if you have, for example, if these are addresses and you have address layout randomization, this would be a way in which you leak the value of important pointers that will tell you for a certain execution where the stack is. But also there are, of course, the less known fact of printf. And this is kind of implementation dependent. You can find certain implementation of printf that do one thing and other that do not one thing. One interesting is that you can reference directly an element in this number of variables. So instead of going in order on the stack, you can say, oh, I want to refer the 4th parameter there in the back, okay? And if you can do that, that's very cool, and you can address part of the stack, the parameters. Also, you can specify the amount of characters being printed. You can say print this integer, but print it in 20 spaces. So fill with space up to 20 for this particular value. In this case, it would be a pointer, but could be anything. And finally, the most beautiful is %n. %n, anybody has used %n in any legal program in their lives other than exploitation? I want to hear the story. That must be beautiful. Let's hear it. What was it?
That was an assignment.
Oh, it was an assignment. So it wasn't a real program. Okay. So %n allows you to write in the corresponding variable that is considered an address the number of characters the printf print up to that point. Okay? So look at this beautiful example. You see to hello %n, there's only one parameter, and you pass an address. So when you get to this, it will not print anything, but we'll take this address and store at this address the value 5. Okay? It's interesting to read how this came and how it can be used. Of course, you know, so you want to have some control. You want to store in a variable, oh, I wrote this much up to this point, so maybe you can do alignment and all different things. Yes?
I just wanted a quick clarification. Like the note says this does not cause an argument to be popped from the stack. That's not true. Like none of the format parameters are.
Yeah, you're absolutely right. It's not a pop on the stack. I would say, you're absolutely right. This is confusing. So in the interpretation of the format string, when you have a %d, you say, oh, I am on the first element on the stack. If you need another %d, you pop from the stack, meaning that your position or where you look for moves. When you use this version, it's like direct access. If you do a %d after one of the direct access, you will still get the first element. That's what I meant. There is no actual popping from the stack, but that's a perfectly good suggestion because that's confusing. Is that clear? So, yeah, we will see an example. So look at this vulnerable program, and you know, you had the classic open a file, add a line to the file, close the file. Great. When you add the log, you know, there is a line that is 40K, read from the input, you know, and if it fails, it goes away. If it's too big, exits, so there is no buffer overflow here. And then stores the line, and at the end, say printf f on the file, the line. Okay? And you can see that the assumption that the person that wrote this program made is that it's going to read from the standard input a line of a log and append it to a file. Okay? But the moment he prints the line, the format, if he would have printed %s, comma, the line, everything would have been copacetic and non-vulnerable. But the moment he write this line, it will work until somebody, as a line, puts a %d or a %x, or even worse, a %n, and then you can pop up an address from the stack and store a value here. So you can see that popping a value from the stack and storing a value that you can control is an arbitrary right. So you can do all sorts of beautiful things with this type of thing. And sometimes people get confused, but imagine every time you see a printf, you know, and say, is this vulnerable? You have to say, what is the format? Because the all fprintf or printf means only it will not have this, right? In every case, is the format string under the control of the attacker? If the answer is yes, then it doesn't matter if you have here a bunch of parameters, because you can always add, you know, 50%d that will consume the actual variable in the stack and then go further. Okay? The important thing, remember, a printf is vulnerable if the attacker can control the format string, not anything else. So if you look at this, you know, if you call format simple, the program that we just see, you do echo test line pipe format simple, it will print test line on the standard input. It will read the test line, and if you do tail-shell temp log, will show what's into that file. So that first two lines show that if you pass on the standard input test line is added to temp log. Okay? Then what happens if you write test line %x, %x? Same thing. But now you have test line 1, 0. Does 1, 0 It's just because printf decided, oh, two formats, let's go on the stack. Above me, somebody put an integer. Oh, it's a 1, let's print it. Oh, it's a 0, let's print it. And so fundamentally, you can go up the stack and do whatever you want. So let's do more. Let's print a string that has the value A, B, C, D, and then let's print 8 pointers. Okay? So let's go up 8. So the string will be A, B, C, D, then 8 pointers. 1. Oh, there was a 1 there for some reason. Great. 2, 3, 4, 5, 6, 7, and 8. But these have some familiar, aspect, right? What is 41? In ASCII, hexadecimal 41 is uppercase A. So here, we went up to the stack up until we reach our own string. This is uppercase A, uppercase A, uppercase A, uppercase A, just interpreted as a 32-bit integer. This is B, of course. This is C, of course. And this is D. So we're going up to the stack. So we pass as a parameter to printf a string, okay? And we had enough percent that we went up the stack, and after a bunch of crap, we reached this, okay? That's awesome. Why? Because we control this, okay? So we have 4 pointers that we control. So if we actually, at a certain point, right when we're here, we start doing %n, we're going to write everything that we printed in number of characters printed up to that point at this address, and then another %n character printed on this address, at this address, at this address. If between address we write more characters, which also we control because we control the whole format string, we can do 4 arbitrary writes, which, done in the right thing, will allow us to write in the return address wherever we want, whatever pointer we want, which happens to be our shellcode. For example, in the environment, or if this string, the thing that is before here could be the whole shellcode for what we care. Okay? So, let's look at how we exploit this. First, in our GDB session, you look at the environment and you look for egg equal, find this string. So that we know where in our environment is. We find, oh, look, I found that at 0FF, D374, there is our shellcode. Actually, you add 4 just to skip the EGG equal thing. Okay, so actually our shellcode is at 378. Great. Now, the addlog function, okay, we have to overwrite the return address of that function using consecutive writes. Okay, so if you look at where we are in EBP, if you print 2 integers at EBP, you will always find the save EBP followed by the. There's moments like, are they really listening to me, or they're completely zoning out thinking that this is. Okay, do it. What value is this? Every time I do this, wherever I am, what value is this? Oh, I love this. Very good. It's the saved return address. So if I say print whatever is in the EBP points to a cell that contains the saved EBP, followed or preceded, because we're going, followed by the return address. So this is the return address of the caller to func. This little pattern is very useful. Wherever you're in a function, you find what is the frame pointer that has been saved, and where are we going to return when we're finished with this function. Okay? So now, this value must become our shellcode, which is the environment, the address of egg plus 4 to account for EGG equal. Okay? Therefore, we have to write the bytes FF did 3 and 74, and 78, of course, in reverse order because it's little endian, and we have to remember that, otherwise it won't work. So how do we write these 4 bytes? Well, there are various techniques that you can do. There is one that is pretty reliable, which is to write 4 short integers. Why? Because you can control, by writing 4 integers, you can always control the lower end byte. This is, again, little endian. So the least significant byte comes first, and then the most significant byte. So if you have something that is 85, BB as a short, we need a short integer that ends in 78, because it will be some crap 78. The following short will overlap, and we only care about the last one, who has to end up in D3. And then we have something that has to end up in FF, and again in FF, so we don't have to do anything because it's the same value. So you write it twice. So the cool thing is that the overall number of characters written always increases, right? So one way to do it would be to write just 2 shorts, one here and one here. But what if those 2 values are not in the right order, one before another? It can be complicated. This is very reliable. You can write byte by byte, and the only thing that you care is that the end of your short value is the desired value. And so you can always reach it, because you can write enough characters so you get exactly there. You can also switch pointers, but they're all different things. So we want to do 4 writes, imagine. This is our, CC/EBC is where we have stored our return address. Now, at this address, we have to write a value that, let's say the first one, something that ends in 078. So we will start the string with 4 addresses separated by characters. So we'll have something, an address, some stuff that we don't care about, another address, some stuff I don't care about, another address. And since we don't have to change FF, we have the same address again, We don't have to have anything between the 2. These are, if you look at these addresses, this is like FF, CE, BC. FF, CE, BD, so the following 2. FF, CE, BE, the following 2. FF, CE, BF. These are the 4 addresses of these 4 shorts that we're trying to write. So we need to pop up 4 parameters to reach the addresses. Remember, there was the 1 and the nil. So we have to just throw that stuff away by writing, something. But while we're popping them out, we use this value, to get to a short value that ends in 78. 78 in decimal is 120. So fundamentally, we have to pop out. So I asked to print 4 integers. I don't care about them. 1 is 1, 3 are null. I don't care. But I want them to be written in 20 spaces, 20 spaces, 28 spaces, 28 spaces. And at this point, we have printed 24 characters of this, plus additional 96 here, So in total, 120. So at this point, we pop everything we care from the stack, and thank you to these little spacers here, we have reached in the number of characters printed out exactly 128, Now, at this point, we are just going to say, hey, write h is a short value at the address. So the next parameter is this one. It will be taken as an address, And at that address, they will write a short, which is 120. So 78. 0x78. It's going to be 0078. We don't care because it's going to be a little endian. It's going to write the 78 exactly where we want, and the 00 we don't care because it's going to be overridden for the following one. Now we need a value that ends in D3, but it has to be more than yes.
You said this is little endian. What
yes.
Endianness does Intel chip have? Like
little endian.
It is little
Yes.
endian?
Yeah. So now we have to write a value that ends in D3 because we have to write 78 and then D3. We wrote 120 so far. We have to get up to 211, which is D3. Now we have to produce 211 minus 120 characters, so 91. So we say, hey, write an integer, which is A, and that's why we put those 4 A's between addresses. So after a write, we can adjust the number of characters written and then do another write. Here, 91 character, and then write another host. After that, we need something that ends with FF. So anything, but we have 255, we're lucky. It's simple. We need only 44 characters. So you do 44 and you write. And since the character count hasn't changed and you want to write another FF, you simply repeat write the host. So eventually, the final string is first address, some stuff to add some count when we print with the % format. Another address, something else, another address, and then all the stuff that we need to trigger everything. And by this point, we overrode the return address. When the function returns, we had, code execution. Okay? I know it sounds complex, but it is a little bit complex. But eventually, the only way to really understand it is you will have to do one for homework 3. So it's actually super fun. Yes?
So you did, in practice, you have to make these number of characters dynamic because the address that you're writing to may be different depending on.
Yeah, I mean, yes, meaning that, so this is the assumption that your stack is not moving around, okay? Otherwise, you would need probably a leak. So first, find out what the stack is using the same technique, and then calculate, have a script that interacts, gets the address, build the strings so that you know exactly what you do. But the basic idea is that with this technique, once you have control over the string, you can overwrite whatever you want, wherever you want. It's a super powerful attack because there is no, string canary or, it's just an arbitrary overwrite. Arbitrary overwrites are much more powerful than, for example, buffer overflows. Because buffer overflows sometimes, they destroy the stack. And it could be that because the stack got destroyed, suddenly your stuff doesn't work anymore. So even though you have an overflow, you can crash the program, but it's not exploitable. Suppose that you have a buffer overflow, and here there is a thing it happened to me in situation where you have a buffer overflow, and before it returns, it checks that a local variable that you smashed with your stuff is equal to 0. And if it's not equal to 0, exits. Then you're ruined. Why? Because your buffer overflow used string copy. So you cannot embed a 0 to account for that variable and reconstruct the stack the way you want. So even if you can smash everything you want, you cannot exploit that vulnerability. Maybe there is another one. You can override another variable. It doesn't matter, but not that one. Okay? This is an example of a real-world attack. There was this localization system that allows you to fundamentally all the strings in the operating system, instead of saying, command not found, tells you comando non trovato, in Italian. That would be super awesome. So you can actually have, something that points to how to map these messages in various languages. The cool thing is that you could specify a language using an environment variable, okay? The awesome stuff is that there was a vulnerable implementation where you could use a ... attack to specify your own version of the localization messages. And so you would create a fake localization message. And for example, you would have, instead of invalid option, you would have something, you would recognize, some of these numbers. And this is something that would pop from the stack a bunch of things until it gets to, the right values, and it would just write whatever it's needed, wherever they want. So it's a composition of a cool, confusing the deputy by using a dot attack. So it will use a localization message under your control. And since the localization message does the printf, and these are the format strings for all the printf in the various languages, you can put whatever attack you want as a format string and execute them as root. So lesson learned, whenever an attacker can control the format string, you're in trouble. Most implementation right now, if I see a %n in a string, that would scream bloody murder. And there are various protection for it. But once again, never assume you have to know these attacks, because there will be plenty of implementation that you will see where this is actually, you will see instances of this type of attack. You can see here, for example, remember, it doesn't matter if there is one or more parameters. It's all about who controls the format string. So if the format string in this case is a constant, so you cannot modify this. This is safe. You can, whatever you print is up to you. But here, you cannot modify it. In this case, you see, you have buff and you have the two variables. If you still can control this, even though you have the variable, it's still bad. This is something that sometimes you get confused during the final. There is a classic example. Is this printf vulnerable? You have to know it's vulnerable because I can control the format string. I don't care if you have variables. If I control this, instead of having %d for this two, I will have 55%d. And I'll start, going on the stack, getting values. Is that clear? Very good.